Good afternoon, Los Angeles, and to the whole world watching YouTube. If you're watching, okay? My topic this afternoon is plane areas. We will derive the formula for taking the area of an ellipse. The general formula for taking the area of an ellipse. Okay, let's proceed. This is pure derivation, an application of integral calculus. Plane area, lesson number 50 on my channel on my topic integral calculus. I will read the problem. Derive the formula for the area of an ellipse with major axis A, minor axis B. The dimension of an ellipse is actually the major axis designated by A and minor axis designated by B. Ellipse is something like it looks like a circle, okay? Because actually circle emanates from the ellipse. Okay, let's try to bring out the figure. Y-axis, X-axis. To simplify calculation, we will just draw an ellipse with center at 0, 0, with center at the origin, 0, 0. Okay? The major axis is A, and the minor axis is B. The major axis is actually parallel with respect to the x-axis. The bigger dimension is actually parallel with x, and the smaller dimension, which is referred to as minor axis, is parallel to the y-axis. Actually, this is the equation of an ellipse with center at 0, 0. If you try to recall your analytic geometry. To draw this one, it is a simple matter, you know. When x is 0, when y is 0, from this equation, when y is 0, this will become 0. Okay? So x squared now will be equal to a squared times 1, or x squared will be a squared, or actually x is actually plus and minus a. So when x is 0, the value of the value of x is a and minus a. This is the right hand side, this is the left hand side, plus and minus. And when y is 0, when x is 0, you place this as 0. Y squared now will be equal to b squared times 1, or y will be the square root of b squared. Y will be plus or minus b. When x is 0, the value of y is plus b, and this is minus b. So actually, if we try to interconnect the 4 points, this is an ellipse now. That's the complete ellipse. Okay? So it's a must that you know your analytic geometry, and it's a must that you know how to plot your graph on the Cartesian coordinate system. Okay. The equation of this ellipse is actually x squared over a squared plus y squared over b squared equal to 1. Okay. And by using vertical slice, we will draw a vertical slice over here. The thickness will be dx, and the height, okay, it's a variable height, because as the value of dx moves from 0 to a, actually the height is variable. It varies. That's why do we know it varies? It's a variable equation, right? It got an equation, it's not a straight line. So it varies. So actually, the variable height is actually the difference of this upper y minus this lower high. And this lower high is actually constant from 0 to A. Actually, y lower is actually 0. Actually, we are given that one. At H, a straight line. Okay. But how about the y higher? Y higher refers to the variable y of the ellipse. We will try to compute y from this equation here. So actually, if we now try to bring out the differential area is y higher minus y lower times dx. But y higher for the meantime we do not know. Y lower we know it. It's a horizontal line, okay? And the equation is just a simple one because y lower is 0. Okay? Solving for y higher. Solving for y higher. From the equation of the ellipse, x square over a square plus y square over b square equal to 1. Try to compute for y square over b square. Okay? We let it remain on the left, then we transpose this one on the right. So on the right will be 1 minus the transpose value of this, x square over a square. And if we try to simplify this one, 1 times a square is a square minus x square over a square. That's the simplification. Okay? Solving for y square, multiply all terms by b square. Left and right, multiply by b square. Y square over b square times b square, this will cancel out. What remains on the left will be y square. B square times this quantity will be b square times the simplification of this, which is a square minus x square over a square. And taking the square root of both sides now, or raise both sides of the equation to the 1/2. Y square raised to the 1/2, these two here cancel with this. What remains on the left will just be simply y, and this will be equal to b square times this, the operation is product, and we are taking the square root. So b square to the 1/2 will be, actually this a square we could place it here now. Right? Then combine this one, then take the square root. What will come out will be b over a. Since the operation is a multiplication, what will come out for this one, if we raise it to the 1/2, will just be simply the square root of a square minus x square. But what is this y? This y here is actually y higher. It is the y at this point here. Because as this differential strip moved from 0 to a, this height here is variable. And it is designated by this. It varies. Okay? Going back to the differential area now will be equal to, by using symmetry, to take the total area of the ellipse, just take 1/4, then multiply it by 4. Okay? So I place it here, differential area over 4 equal to, what is y higher? Y higher is this, b over a times the square root of a square minus x square minus 0, which is y lower, times dx. Actually, this is now 0. So actually what comes out is just simply this value here multiplied by dx. And we are now given differential area as a function of x. Okay? Single variable x. So to compute for the area, take the integral of both sides. Okay? If we now try to take the integral of both sides, okay, for b over a is constant, we can bring it out now. If we take the integral, the thing on the right hand side, this will be the integral of the square root of a square minus x square times dx. The integral of the differential area is just the area, excuse me, equal to 4b over a, the integral. The value of x moves from, for a 1/4 area, it will move from 0 to a. So the limit is 0 to a. the integral of the square root of a square minus x square times dx. To solve for the area, bring out the integral of this by any means necessary. We pass by the integration of differential calculus, different equations under differential integral calculus. So use your knowledge of integration. And I think the proper solution for this is by using trigonometric substitution. We will let x squared equal to a squared sine square of theta. We try to look the one inside. Okay. Taking the square root of both sides, x now will be a sine of theta. Taking the differential of both sides, dx now will be a cosine of theta differential theta. A is constant. Sine of theta's variable should be a times the differential of sine of theta, which is cosine of theta differential theta. Let us try to solve the value of the square root of a square minus x square separately to be more systematic on the solution. The square root of a square minus x square equal to the square root of a square. X square is actually, from our trigonometric substitution, it is a square sine square of theta. Okay? I expedite a little bit the solution, so I will show you how. Just take a moment, guys. I will erase this word so I could write nicely and you could see it clearly, you know. It's all about systemacy. If you are not systematic and you are not clean in your solution, it's hard to... Okay. I'll continue with this one. The square root of a square minus x square equal to the square root of a square minus a square sine square of theta equal to the square root. We factor out a square. Then this will be 1 minus sine square of theta equal to the square root. The operation inside is multiplication, a square. 1 minus sine square of theta is cosine square of theta. Perfect square, we're taking the square root, what will come out will be a cosine of theta. It is a cosine of theta. Okay? So if we now try to integrate this one, we'll go back. Okay? Therefore, the integral, I will integrate this one also separately. The integral of the square root of a square minus x square times dx equal to the integral. The equivalent of this is from that one. It is a cosine of theta. Dx is actually cosine of theta, a cosine of theta, differential theta. A times a will be a square, that is a square, we bring it out. Cosine and cosine, that will be cosine square of theta, differential theta. Okay? This will be cosine square of theta as a function of double angle. This is the equivalent. Okay? Try to recall your trigonometry. Cosine square of theta as a function of double angle is 1/2 times the quantity 1 plus cosine of 2 theta differential theta. Okay? We bring out 2, a square over 2. 1 times differential theta is differential theta. The integral will be theta. The integral of cosine of 2 theta differential theta. The integral of the cosine, there is a formula. But the value of u is twice theta. du will be equal to twice differential theta. So actually we are missing 2 over here. So we place 1/2 outside. So the integral of this will be 1 over 2 sine of 2 theta. The integral of a cosine is sine. Okay? With the limit, this is theta for the meantime, theta 1 to theta 2. We could eliminate theta 1 and theta 2, okay, by just replacing theta in terms of x. From the value sine of theta is equal to x over a, where did this came from? It came from this. Okay? X is actually equal to a sine of theta, therefore sine of theta will be x over a. So if we draw a right triangle, sine of this angle is opposite over hypotenuse. So this should be x and this is a. The adjacent side will be the square root of the square of the hypotenuse minus the square of the opposite side, then take the square root. Okay. Then we try to calculate the value of this one. Okay. 1/2 of sine of 2 theta is 1/2. Sine of 2 theta as a function of a double angle is 2 sine of theta cosine of theta. So these two here cancel with this. What will come out? 1/2 of sine of 2 theta, if we go back there, it will be sine of theta cosine of theta. But we know sine of theta from this. We know cosine of theta from this. Sine of theta will be x over a. Cosine of theta will be the square root of a square minus x square over a. Okay? A times a is a square, that's on the bottom portion. X over a square times the square root of a square minus x square. So if we go back to the final formula for taking the area, we'll go back here. We'll follow this. Total area now will be, we got a 4 here because we removed this 4, we put it on the right already. So this should be 4b over a, okay, times the integral of this, and which we take it separately. It is actually a square over 2 times this. Okay, or this should be a square over 2. Theta is arc sine of x over a. Cosine of 2 theta as a function of a single angle is actually x over this, x over a square, times the square root of a square minus x square. This is sine of theta, this is cosine of theta, this is theta. So our limit now, so the variable now inside is actually x, so we could bring back the original limit from 0 to a. This is from 0 to a. Okay, I simplify this one a little bit, guys. This should be, what will come out? This 2 here, 4 here, cancel with this. What remains is 2. 1a here, cancel with this, 1a. So this should be 2ab. 1 times 1 is just 1, or 2ab times. Let's now try to put the upper limit. Arc sine of, when x is a, this will be a over a. Okay? Plus, when x is a, the 1 in the radical will be a square minus a square. Okay? The square root of 0, 0. So, 0 times this one will be 0. So, the second part of the upper limit will be 0. Minus open quantity. We put the lower limit. Arc sine of the arc sine of 0 over a will be equal to 0. Okay? And the value will be equal to 0. What angle in which the value is 0? It's 0. So this is 0. Okay? And when x is 0 for the second part on the lower limit, this will be fine because this will be a square minus 0, right? But when the value of x is 0, this will become 0. 0 times a will be still 0. So the second part of the lower limit will be 0. So actually what will come out is just simply like this. This is now 0, I could remove it. This is now 0, both the value of the lower limit times this. Okay? And the arc sine of a over a is actually what angle in which the value is, the sine of its value is 1. It is 90 degrees. So the arc sine of 1 is actually pi over 2. Okay? What angle in which the value, if we take the sine value of a, it will be 1. It is 90 degrees. But we will take the equivalent of that in radians, and that will be pi over 2. So 2ab times pi over 2. So these two here cancel with this. So the final formula for taking the area of an ellipse as a function of the major axis A and minor axis B is actually pi AB. It is pi AB. Actually, the formula for taking the area of a circle emanates from this. I show you how. Because a circle is a special case of an ellipse. For a circle, the radius R is actually equal to A equal to B. So from the area equal to pi AB, okay, for a circle, A is equal to R and B is equal to R. So if we try to substitute it from this equation here, area of a circle now equal to pi times R. Or area of a circle is equal to pi R square. So the formula for taking the area of a circle emanates from the area of an ellipse, because a circle is a special case of an ellipse. That is, when the value of the major axis is equal to the value of equal to the minor axis, and this will be equivalent to R for a circle. Okay, guys? That's the derivation for the formula for taking the area of an ellipse as a function of the major axis and minor axis. I repeat it for the last time. Area for an ellipse will be pi AB. Square units. Ellipse will be something like if we are watching the Super Bowl. If you try to